Okay, this is Technical Technician from Diagnation talking about air-fuel ratio sensors. And we have to realize they are a different animal than the old school zirconia oxygen sensors that we've dealt with for so many years. On this particular Honda 04 Honda Accord, the upstream sensor is an air-fuel ratio sensor. It's commonly referred to as a critical current sensor. It has 4 wires. It looks identical to an old school oxygen sensor as far as size, thread, connector. It is different. There are situations I've seen in case studies where a car rolled off the assembly line with an air-fuel ratio sensor, and it inadvertently got an oxygen sensor, and I've seen people run into that dilemma. If you ever think you're there, I would unscrew the oxygen or whatever sensor it is and look at the part number and Google the part number, and you may hit pay dirt as far as what the sensor actually is. Just anyway, this sensor is different. It is pre-catalyst on this vehicle. As we key in on it, it's got 4 wires to it. It's got the same heater, although heaters on air-fuel ratio sensors draw more amperage. They run hotter. Heater is ground side controlled by the PCM. What we have is there are 2 bias voltages the PCM sends out to the air-fuel ratio sensor. It sends out on Honda. On this one, it sends out, that's a typo on my part. Looking at that should be 2.2 volts. Okay, the lower one is 1.8 volts. Anyway, different manufacturers on these type of sensors do it different. Toyota likes 3.3 on one wire and 3 volts on another wire. Nonetheless, in this case, we're looking about 2.2 on one feed, and on the other feed is 1.8 volts. Okay, we will not look at those voltages. We're going to do something different. We're going to use only 3 channels with a high sampling rate. We will be looking at the voltage drop across the sensor. In other words, the net result of those 2 voltages changing, because that PCM will pump current in one direction or the other direction to infer the fuel mixture. I know that there's something internal to air-fuel ratio sensors. It has its own little oxygen sensors that the PCM wants to pump as much current as to get that oxygen sensor back to stoke, to 4.5. I won't get into this. I don't really know that much about these sensors. They are complex. There are other types. There are 5 and 7 wire sensors. I believe they call those a pump cell. In this case, we're dealing with a critical current 4-wire air-fuel ratio sensor. Our hookup is as follows. Channel A, we are across the air-fuel ratio sensors at the PCM. We will be dealing with a range of about maybe 300 to 500 millivolts. That will be the voltage drop across the sensor because, as I said, it has 2.2 volts on one side and 1.8 volts on the other side. If I hook into those wires and looked at the 2.2 and the 1.8, those voltages do not change when fuel mixture changes. They're going to stay steady, and I've tested them. I've seen other people test them. They are rock steady. Just want to make a point out. This is not the speediest way to check these sensors. It may help if you think you have one wigging out on you intermittently or something. It's just an idea to get the scope side of an air-fuel ratio sensor. The real gold standard way is the scan tool, and on part 2 of this video I will upload a scan tool capture in exact sequence as I was taking the scope capture. I had a scan tool recording in the background. That is on a Blue Driver. It's basically a OBD2 base scan tool hooked to my cell phone. We're going to look at 4 PIDs in part 2. We're going to look at O2 sensor, bank 1 sensor 2. That is a downstream zirconia sensor. The next PID is a wide range equivalence ratio, which to be honest with you, I'm not quite up on. It is somewhat similar to lambda, where if the mixture is north of 1, we are lean, south of 1, we are slightly rich. The third PID is the bank 1 sensor 1's current. That will change with mixture. And the 4th PID is bank 1 fuel trim, short-term fuel trim. Anyway, our second channel is we're going to look at the downstream O2 sensor on the scope. And the third channel, we have a micro clamp hooked to what Honda calls the positive air-fuel sensor wire coming out of the PCM going to the air-fuel ratio sensor. I am in the direction of current flow leaving the PCM. Nonetheless, I can't claim that I can give you perfect advice on how everything works. Basically, we're just going to run through the scope and look at the difference in as the fuel mixture changes. As I recorded this video, I did change the fuel mixture. You will see changes in part two. You can hear me saying when it actually went lean and then kind of went back to normal. I didn't intentionally go rich. I went from normal to lean and then back to normal. Anyway, we will look at the scope and talk about it. I don't take everything at face value when we look at things. This is sort of a experimental type video. We know that still the best way to look at these things is with the scan tool, but nonetheless, we never want to sell the scope short if we have a situation, because the scope is a direct quantitative measurement as opposed to process information on a scan tool. Anyway, I can tell you about all these signals. There's a lot of filtering and a lot of vertical zoom, because we're looking at very small signals that don't change a lot. We'll start out with going back to, we were on the first capture. We're at, I was at 2 seconds per division, a long time base. Channel blue is, as you look at your illustration, is right across the air fuel ratio sensor. So that's going to be a millivolts. It's going to ebb and flow. You can see some swings already, as you see on the screen when we go rich to lean. Channel B is the downstream O2 sensor, which as you look at this, and now the car, as you look at this car is hot and it's in closed loop. Somebody needs a catalytic converter, and his initials are MF. Okay, nonetheless, that is not helping matters, but then again, maybe it will help matters as we view this. That I wish that was more of a like your typical good downstream zirconia O2 sensor waveform. It would not have that much action. It shouldn't have that much action. Nonetheless, that's my dilemma, and I will deal with it. Anyway, here we go. We're going to go down the line. We'll kind of take the first situation. Let's look at this big swing here. We have a blue is seems to have a sort of a high and low as the mixture corrects. We have a wild swing on blue. Something pretty radical happened there. We had a voltage change, as you can see from, let's look at the delta. That's about 98 millivolts. Not a big swing, but then for this kind of sensor, I would say it was a big swing. Top to bottom on that, we're looking about 156 millivolts. Anyway, that is the blue channel. The green is the current. Now that is current flowing, and we can see that sort of mirrors blue. That is a small amount of amperage. I can tell you that that delta is about okay. That is 1.224 millivolts. That is 1.224 milliamps, and for that, these sensors, that's a lot. Okay, I can tell you, they don't usually swing that wild. Something pretty radical happened to the fuel there, and it probably made its adjustment, and it leveled itself out around here. Current, if I go back to green, let's look at the delta on green. We're going to get into microamps. Okay, that's there we're looking about 350.4 UV. I believe that is microamps. It is not milliamps. It is a very small value, but nonetheless, look at the if you could try to make out some ebb, some high and low, it's very subtle on green as I roll the mouse across. Channel red is our downstream O2 sensor, and we can definitely see relationships between everything here. As the O2 sensor goes high, our blue guy sort of goes down, and then it comes up, and then the downstream O2 sensor goes down. That is our voltage drop across the air fuel ratio sensor. We got one more wild swing there. We can see we went rich here. This is where it probably got its fuel back, and I probably don't have the best scaling. Believe me, that's negative 550 millivolts. If I look at the bottom on it, is much more. It's let me just move that, and this guy is. Okay, that's negative 982, so it is more negative. It is more, would imply more lean. The current, nonetheless, goes in the direction of, I would say, negative. You can see 171. there, and you see about 967 there. So it's actually going more negative as the mixture is going, looks like to be going richer, but that is up for debate. Please chime in on these sensors. Anyway, I want to get more vertical zoom on blue, and we will see that. Okay, actually we can look at blue where it looks kind of more similar to what a conventional zirconia, but it is, as I said, is not a conventional zirconia. Let's look at a more normal pattern when we don't have such a wild swing. Let's see what it looks like. We can see something which would apply as normal. Take a look at blue, and I want to count. They always taught us that a conventional oxygen sensor should make, what, 8 swings in a second, 8 to 10 swings in a second. Let me count 10 swings and see how long it took. Okay, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Alrighty, that is 6.1 seconds. So obviously that I wouldn't compare that to a normal zirconia oxide right off the bat. That is way too long. Nonetheless, let's apply that to green and take about 10 swings and see how long that took. That will put us about right here. That is more like a second. Now, I know this is unconventional, but can we actually interpret that as this thing acting? I don't want to say it's a zirconia sensor. It's a lot better and has a lot wider range for checking fuel mixture. But we can see we got about 10 swings in a second. Nonetheless, that's just something to ponder. We're going down the road. We see another wild swing. Take a look at that wild swing. We got a lot of vertical zoom. The voltage drop across the sensor went really low. That is the result of the 2.2 volts on one end and the 1.8 on the other. Our green guy went low to it, followed blue, and this is probably a rich situation, being the fact that our downstream O2 is high, as high as it can get. So anyway, it's just something to look at. Let's keep rolling down the line and see if we can make any other assumptions here. Here we go a little different. Now we're high on the blue. Okay, we're high on that, and then we're low on red. So we're lean here. But our current really isn't doing much. It's still pumping in and out of that sensor. It's going one way, the other way, one way, the other way, the other way. That's just the way this sensor works. I know, as I said, I'm not an expert in the sensor. It's a complex piece of sensing apparatus. Nonetheless, it does have more range than an O2 sensor, and it's able to make a car run leaner or get more accuracy, as opposed to a zirconia sensor, was basically a switch, which is either rich or lean. This thing is, I guess you would call this more of a variable resistor, to make a comparison. Anyway, those are our scope captures. It's, as I said, it's not conventional. We never want to sell the scan tool short. Scan tool's got really good graphing capabilities and PID catching capabilities. In part 2, you will see the scan data. It is an exact time to this thing. It was recorded right when this was recorded. So anyway, signing off. All the best, and take care.